Whoa. Better back that up. There we go. All right, so we had talked about div and curl, right? The take-home exam, mini exam, is due on Wednesday, right? And there's, the curl of a vector field is a vector. The div of a vector field is a scalar, right? And there's two pretty good results that we can, connections we can make between curl and the line integral over a closed curve. So using Green's theorem, if we're trying to find the line integral over a closed curve C on a vector field f dot dr, then Green's theorem says that that can be switched to what does Green's theorem say? You have this. This f dr equals double over d partial q with respect to x partial p with respect to y dA, right? Well, the curl, okay, the curl right here, if you go back and look at curl, if you look at curl, the last component, the k component, is partial q with respect to x minus partial p with respect to y, right? So if I go back here now, then if I dot that with k, now remember dot product means each component multiplies, then k is the vector 0, 0, 1, then it kills off the first two parts of the curl and just leaves you with that third component of the curl. The third component of the curl is this, right? So that's just a cute little extension that you can look at this right here, this line integral over the vector field on a closed curve, as the double integral over the D region of the curl dotted with the K vector. It's K hat. Yeah, it's K hat. And then there's another extension. Now, we have not seen this. I don't know if you remember when we first established the line integral over the vector field, we initially said dot T, capital T, and it was the tangent. And that capital T turned into our dr. Yeah, you don't remember that? Well, there's other applications that we'll look into them later, that if you want to take the vector field and dot it with the normal vector instead of the tangent vector. So let me draw a quick picture. Back when we first started, if we had a curve and there's a vector field here, okay? So there's a vector field all over the place here. Then what we looked at was that tangent vector, right, capital T. And then we were computing work. And it had to do with the tangent, scaling the tangent, dotting it with the vector field. But you could also look at what's called the normal vector, which is the one that's perpendicular to the tangent vector. And you could do that instead. And if you do that, then the formula becomes this. F dot n ds is going to be the double integral of the div of f. Now, we'll see more of this later, so I just want to point it out now. We'll get to it later, but it's your first introduction to those nice results. All right, as far as identities with curl and div, I thought about different ways of doing this. I was just going to work it out by hand, but I think I'm just going to, I copied this out of the solution so I could just not have to spend 10 minutes writing it down. If we want to show, and this is very similar to like your take-home exam, if you want to show that the div of the vector field f crossed with the vector field g equals vector field g dotted curl f minus f dot curl g, to show that this identity is true, you do with most all identities. You start with one side and you turn it into the other, right? You do not work with it like an equation. You start with the left side, make it turn into the right side. You can also start with the right side, make it turn to the left side, or You can start left-hand side, get to a point where you stop, then do right-hand side, work it to a point where you stop, and those two are equal to each other. Okay, so however you see fit when you do your take-home mini exam problem. This one's pretty straightforward. Div of something is the gradient dotted with whatever it is. Okay, so this is going to be, what are we setting up here? What does it look like? Cross product, right? Cross product, okay? Cross product P1, Q1, R1 is what? P1, Q1, R1? That's, let's say, F. Now, I'm not saying that, but F here is P1, Q1, R1, so that's our components of our vector field. And then P2, Q2, R2 are the components of our G vector field. So when I cross them, I get this determinant here. And I believe what's missing out front here is the del, because this is just the cross. But here's my del. Del right here, 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 my partials. And then if you do the partial here, you have to do this determinant. What's the determinant here? Q1, R2 minus R1, Q2, right? And then over here, this would be P1, R2 minus R1, R2, right? Yeah, you can do it. Well, it's that way that we did it where we covered up one, and it's basically that. Okay, but here's what I want to show you. I want to show you just this piece right here, and how this piece right here turns into this. Then the rest of these, the other two, will work the same way. Okay? So let me show you that. It's partial with respect to x, Q1, R1, Q2, R2. So partial with respect to x, Q1, R1? No. Yeah, Q1, R1, Q2, R2. Okay, we said that's partial with respect to x of Q1, R2 minus R1, Q2. Agreed? Now, when you take the partial of this, right, the partial is a derivative. You're doing the derivative of subtraction. So you do derivative of the first one minus derivative of the second one. Y'all still there? Now here, what do we have? Product rule. You have to take the derivative of a product. See, it's not multiplication here. That's the thing I want to point out. So derivative of a product is the derivative of the first one, which would be what? dq1 dx, or partial. And then times R1 plus, oh yeah, it's R2, thank you, R2. Yes? Then what? Partial R2 partial with respect to x, Q1. You see that? What? Yeah, I changed it up here. I had messed up right here. And then now I do this one, and that's another product rule. So I would have minus, because there's subtraction, partial R1 with respect to x times Q2. Then another minus, because that distributes, partial Q2 with respect to x, R1. Do y'all see that? PQ, yeah, they just subscript them. Questions? Now let me go back over here. So you can see this right here is what we just did, right? That's it right there. Now they did their product rule a little different, but we should have the same 4 terms here, right? Then they did this one, 4 more terms. Then this one, 4 more terms. Then what they did is they basically dropped all these parentheses, and they got all their all their terms with P2, right? Factored out of P2, factored out of Q2, factored out in R2, separated that from all the factors that, all the terms that had P1, Q1, and R1. And if you look at that, this right here, that is exactly G dotted with the curl of F. And the second brackets here is F dotted with the curl of G. So there's some work in these problems. You have to mess with them, and you know it's a little strange at first. My biggest thing was just be careful when you're taking a partial derivative with product rules, because it can trip you up. All right, and that was it for that section. I'd like to spend most of today on 13.6. Let's see, 13.6. What, the identities? Yeah, it's just so you've seen it before, you know, because especially math people, like more math related, you know, you want to be able to work with things in a general form like that. So, all right, 13.6. We have 4 sections. We have 4 days. We're going to do just this section today, and I hope to get through it all. I've been sitting here contemplating back and forth all weekend long how I'm going to approach this, and I'm just going to go for it, okay? We have 13, 6, 7, 8, and 9. Is there 9? You sure? Divergence. Is divergence 8? Oh, there's no 9 in your notes. There's a 9 in the book, though. Yeah. I've never been able to treat divergence. I've never been able to get to divergence and spend an entire day on divergence. I've always had to cram divergence into my last day, so I'd never had like official notes for it. So I will give you something. I'm going to try and go to 9. 13. 13. I've always given the formulas from 13.9, but I've never actually been able to spend time in 13.9. Okay, so parametric surfaces and surface areas. All right. Back in 10.7, we defined vector functions. A graph R of t equals, we have 2 components. These components of the vector function are determined by t. So give me a t, it changes the x component and the y component. If it's in 2D or 3D, we have 3 functions here, then these are curves, okay? As t changes, this starts to draw a curve in 2 or 3 dimensional space. As you might recall, here's a vector function. It's t squared 1 minus t cubed. I change t. It draws these vectors, and if you put all the vectors together, it creates a curve, right? We've seen all this. Here's one in 3D. I changed t. This one did that spiral, right? Or that looked like a spring. Okay, and this one was what, cosine t, sine t, and then the z coordinate goes up linearly, right? So we've seen this. These are curves. Curves in 2 or 3 dimensional space. Now what we want to look at, a new concept, what if the vector function has 2 parameters instead of 1? So instead of having the parameter t, just t, we now have a vector function that depends on 2 things, u and v. Now we're not going to use t so we don't confuse it with curves. We'll use u and v instead. So you give me a u, you give me a v. Those are usually numbers, okay? Then my x component of the vector is determined by both of those. The y component is determined by both. The z is determined by both. And this will be something in R3. If u and t take on different values, then this generates a surface instead of a curve. All of these are called the parametric equations for the surface, the x, the y, the z. Okay? Grid curves. If we hold u or v constant, then, this should say then, our vector equation just draws space curves as we saw in 10.7. So if I say, hey, look, I'm going to hold one of those variables, u or v constant. So just plug in a number for it. Then there's only one parameter then, right? So like if I hold v constant, u is the only parameter, and so it should draw a curve, not a surface, curve. Or if I hold u constant and let v change, I should draw a curve. When you put all these curves together, it creates a surface, all right? But each one of those curves is called a grid curve. So here's a first example. Let r of uv be the vector function, or sine u, cosine v, sine u, sine v, cosine u, with u between 0, pi, v between 0, 2 pi. Do you recognize this? All right, well, here it is. It's a sphere. But let's see why. Should be able to get everything on here. Okay, what I have on the left-hand side is like a domain. Okay, remember u and v are my variables. I can plug different values of u and different values of v. So remember, t used to be like the clock running in the background, and the curve would go off and do whatever. Now my clock is actually two-dimensional, and it's in the background, so I don't normally see it. Okay, so does everyone understand that this grid right here is not the ground over here, okay? It's not the ground. It's just a clock, a two-dimensional clock running in the background. With me? Okay, if I hold v constant, now this is where I am right now. You see that point? My u is 0, my v is also 0. So if I'm at 0, 0, and I plug it into that vector function, I'm up here at the north pole of this sphere. Now I will hold my v constant. Here's v, right? So I'm going to hold it at 0. And I'm going to let my u change. If I let my u change, see it draws that green curve, right? That's called a grid curve. Now if I instead hold my u constant, now my u is not going to move left and right. My v is allowed to change. Then what I do is I draw that circle, okay, like that. If you put all those together, then you get the entire sphere. Do you agree with that? Why did my green one only go halfway? 0 to pi. Right, but will that draw the whole sphere? Yeah, because look at the other one swings it all the way around, doesn't it? So imagine the red one tells you you're going to swing all the way around. The green one is kind of like I'm halfway, and then just spin that halfway, and then you draw the whole surface. If I ask the computer to give me a bunch of the grid curves, it looks like the longitudinal and latitude lines of on Earth, right? Okay. Any questions? All right, so some geometric stuff here. Remember that when we were back with the vector function of one variable t, that the derivative of the vector function gave us a vector, right? Function, another vector function. And if we wanted to, it would represent, if we pick some point in time, at that point on the curve, we have some red vector. That's our derivative vector, right? It's not the capital T, because capital T is normalized, right? It has a unit measure. We scale it by its own length. So as we move through time, on a curve, as we move through time, there should be some red vector sticking off that curve at every point in time, right? That's our derivative. So if we go now and we go to this new idea where we have two variables, u and v, if we hold one of them constant, so like let's say we hold v constant, then we're taking the derivative of the vector function with respect to u. So notice the r with the subscript u. That's like the partial of r with respect to u. Well, holding v constant gives us a grid curve, doesn't it? So I should be able to get a tangent vector on that grid curve. And then holding u constant is a different curve, and I should be able to get a vector off of that curve. Agreed? So let's go back to our picture here, right? Here's our picture. Here's a point. That's where I am right now, okay? I'm going to take the partial of r with respect to u, which means I'm holding v constant. When I do that, I get this green. Here's my curve, right? And I have that green line. Now, I didn't put it as a vector, but does everyone see that is the vector coming off? That green one, right? Then, if I hold my u constant, then I get this vector coming off. Do y'all see that? And if I do them both together like this, then what do they create? They create a plane, don't they? And that plane, how is it related to my surface? It's tangent to the surface. Now, we did tangent planes way back when. Do you remember doing that? We had like a surface, and we had this plane that we could move, and we had the ways of finding it, computational. What's the difference between that and this? Yeah, those were surfaces f of x, y, and we were finding tangent planes. Now, this can be any surface. And a sphere is technically not a function of x, y, right? It's not f of x, y, because it fails like that, kind of like the vertical line test. A vector function draws things that are not necessarily traditional nice surfaces and allows us to still grab tangent planes off of it. That kind of makes sense? So it's much more powerful. Questions? All right. Find the, oh wait, did I give you the formula? Hello? I think it's, did I blow by it or what? No, I didn't. Never mind. I'm thinking something else. Let's work through this. I'm going to help you, okay? Let me find my notes. No quiz. No, I don't have time for it today. Okay. Find the equation of the plane tangent to the unit sphere at the point root 2 over 2, 0, root 2 over 2. So first thing I'm going to do is I'm going to write down the equation of the unit tangent sphere as a vector function. And that was the example I just gave us, wasn't it? So look back in your notes. It was sine u cosine v, right? Sine u, sine v, cosine u. And here our restrictions were what? U was between 0, 2 pi. Is that what it was? Or was it, which one was between? Is 0 pi? Okay, 0 pi on u and 0, 2 pi on v. Everyone understand where I'm getting this from? Pardon me? I'm giving you the answer. All this is the vector, right? This is just the vector function, right? Okay, let me try and help you out here. Let me go back to this picture. I want to find the equation of that plane, don't I? Okay, what do you need to find the equation of a plane? Point and a normal vector, right? The one coming off perpendicular? But how do you find the normal vector? How can you find a normal vector? You can cross two vectors that live on the plane, right? Well, if you go back to the note we just had here, those two partials, right? Those two partials, RU and RV, R sub U, R sub V, are two vectors that are going to live on our plane. So if we cross those, we get our normal vector. Do we have a point? We do. The point's given to us. So all I need to do is come up with the normal vector of this plane, which means I need to take the cross product of the two R sub U and R sub V's. But to do that, I need to know what R is, right? So there's what R is. So what is R sub U? Partial of that with respect to U. Cosine U cosine V, cosine U, sine V, and then negative sine U. Is it too dark? You want me to turn the light on? Anyone want the light on? No? All right, what about the partial with respect to V? So I'm back up here, right? I'm looking at that again. What's the partial of that with respect to V? Negative sine U sine V, then sine U cosine V, and then 0. Now, we could right now figure out what the vector is at that point. What's wrong? Well, yeah, you're not going to want to, but I think I'm going to try it, okay? Here's the thing. We could right now use our point, right? Because we have a point. It's root 2 over 2, 0, root 2 over 2, right? We could plug those values in. Well, we could figure out what U and V are, I should say. And then from there, we would have actual vectors, right, with numerical values, and we could cross them. But it's useful for us now to learn how to cross these things without numbers plugged in. So let's cross these in general. So what's RU cross RV? All right. Well, what's the I component? So remember what we did was we covered up the I's, right, like this. And then we did this. We did this times this, right? Determinant here. So this times this is 0. And then minus this times this. But this is already negative, right? So it becomes plus. So what? Sine squared U cosine V. Okay, that's our first component. Wait. I'm going to get rid of those blue things. Sine squared U cosine V. Now we want to find the J, right? So we don't look at these. And isn't J, we just have to remember to put a negative, right? Or do it backwards, however you want to do it. But I'll do this times 0, right? This times 0 is gone. And then I do this times this, which is going to be a positive. Well, is it negative? It's positive because remember, with the middle component, it's backwards. So depending on how you do it, I mean, I just do it the way I normally do it, and just remember that I don't, I'm going to change the sign. So this should be positive when I'm done. Instead of it being minus, it's 3. Well, but then the one outside, yes. So it's 4, yes. Everyone has to have their own way of feeling comfortable with this if they're going to do this method. The other way is to do it the way I showed. Yes or no? So what is this going to be? Sine squared U sine V. All right. Sine squared U sine V. If you want help on that, let's just come out to my office and we can talk about it. All right. Next thing. The K. So we're gonna ignore K, right? And this is a traditional, from here to here minus from here to here. So, cosine and then cosine U sine U, right? So I'm going to do cosine U sine U cosine squared V minus, but then it's going to become plus, because one of those is negative. And then what? Sine squared V, and then cosine U sine squared V. Okay, so that again was this one times this one minus this one times this one, but the double negative would make it a positive. All right. That is the cross product, right? That's the cross product. Does any of this clean up? The third component, right? This is sine squared u cosine v, sine squared u sine v. The last one, what can I do? Factor out this from both. When I factor those two out, I'm left with the cosine squared v plus sine squared v, which is a 1. So all I have is a cosine u, sine u. All right. We just did that to get practice with it. That's all we did, okay? What I'd like to do now is figure out what these vectors are. So what do I need in order to determine what this cross product is? What do I need to know? What u and v are, right? What u and v are. So how are we going to figure out what u and v are? We have to go back up to the original vector function, and we need to say, hey, look, what point are we supposed to be at here? We're supposed to be at root 2 over 2, 0, root 2 over 2, right? Yes? What u and what v do I plug in here in order to get these three coordinates? It's going to take some just investigation, just looking and trying some different things. I would start with this last one, cosine u. Cosine of what is square root of 2 over 2? Pi over 4, is that the only thing? Where else is cosine root 2 over 2? Yeah, it happens in the fourth quadrant, but look at the restriction on our u. It's between 0 and pi, so the only place it happens is at pi over 4. So I know that u must be pi over 4. All right, now that would make this, what would happen here? What is sine of u? Now, u has to be pi over 4, right? What is sine of u? So what's sine of pi over 4? Root 2 over 2, which means I need this to become a what in order for that to happen? I need that to be a 1. Where's cosine 1? At 0, right? 0 and 2 pi, but our restriction is this. Well, could it be 2 pi? It won't matter, right? Because they're going to give you the exact same thing. So 0. Is that okay? So let's see. Let's just check that the middle one works. What's sine of u? Well, what's sine of pi over 4? Root 2 over 2. And then sine of v, what's sine of 0? 0. So this is our u and this is our v. Got it? Now what we do is we come back down here to this cross product, and let's plug in our u and our v here. So Ru crossed with Rv equals, okay, sine of u. U was pi over 4. Sine of pi over 4 is root 2 over 2. Square it. Root 2 over 2 squared. 1/2. Times cosine of v. What's cosine of 0? 1. Okay. Sine squared of u again. 1/2. What's sine of v? 0. Next. Cosine of pi over 4, root 2 over 2. Right? Sine of pi over 4. Root 2 over 2. Root 2 over 2 times root 2 over 2. 1/2 again. So the cross product is 1/2, 0, 1/2. But the cross product is our normal vector for our plane, isn't it? And we have a point on the plane. So going back to the standard old equation of a plane, if you have the direction vector of the normal, remember it is a x minus x naught plus b y minus y naught plus c z minus z naught equals 0, right? I know what a, b, and c are, right? A is 1/2, b is 0, c is 1/2. And then x naught, y naught, z naught is root 2 over 2, 0, root 2 over 2. So our equation should be 1/2 x minus root 2 over 2. B is 0, so that's gone. Plus C, which is 1/2 z minus root 2 over 2 equals 0. And that's an equation of a plane, isn't it? I mean, you could distribute the 1/2 through, you can multiply both sides by 2, clean it up. The cleanest version I got it to was x plus z equals root 2. That is the equation of the plane tangent to that sphere at that point. The power of this is that you can find now the tangent plane to any parametric surface using this formula. Using this idea, I should say. All right, questions on that? We okay? All right, surface area. This is actually pretty cool. Given a surface S with parametric equations, with parametric equation R of uv, look at this notation, with U and V in D. So remember how I said the domain was sitting on the side there a second ago? It looked like a little rectangle? Well, that's now our D. Our D is our rectangle on the side. So if we want to know the surface area of a surface on that rectangle, on that domain, then it's going to be the double integral of this. What is this? The magnitude of the cross product. Do you remember what the magnitude of the cross product of two vectors gives you? The area of the parallelogram spanned by the two vectors, right? Yeah? So check this out. Let's say that I'm trying to find the area of just that little piece of the sphere. Okay? So what I'm going to do is I'm going to grab my U, I'm going to move it around here. Now, grab my V and slide it around here. So that green is the area of the cross, well, the area is the cross product of those two partial derivatives, right? So one of these is a partial, one of these is a partial, right? There's the area. The area is not a very good approximation, is it? To the red part I want? And if I turn it, you can see, well, I'll do it in a second. But what we can do now is we can take this and go infinitesimally small as an approximation, right? You do it on infinitely small rectangles. And what happens is that becomes a good approximation. And let me see if I can do this. You can see my little plane is not exactly on the surface, right? But it is a damn good approximation of that red, okay? And that's the whole idea, is that in the limit, as you let the number of these go to infinity, this will be the approximation we need. All right. Find the surface area of the unit sphere. Now we all know what the surface area of a sphere is, right? It's written in some formula in some book, right? The surface area of a sphere? 4 pi r squared? 4 pi r squared? You believe that? So whether or not you look it up in the formula, whatever. What we want to do is find the surface area of a sphere using what we just learned, all right? And it should match what the formula is. It's a unit sphere, which means the radius is what? 1. Okay, that's important. So if I do a unit sphere, the parametric surface vector function is the one we just had, right? What is it? Sine u. So it's the same thing we just had, right? Sine u cosine v sine u, sine v, cosine u. Now what we need to do, and let me point one thing out to you here, all right, just so everyone's clear on this. Had the radius of this thing been something other than 1, because it's a unit sphere, we would have to account for that change in radius, and that change would go right in here. Okay? It would be like A or something, or R, or rho. So if the radius, if we wanted to know the surface area of a sphere radius 2, then we would put 2 in here, 2, all right? But we're doing the unit sphere, which makes it nice. So in order to find the surface area with our restrictions, right, our restrictions were u's between 0 and pi, right? V's between 0 to pi. Then what we need to do is take the double integral over that region of the magnitude of the cross product, RU cross RV, dA. We just found the cross product, didn't we, in the previous one? So let's just work with that. The cross product from the previous work we just did, what is its magnitude? So I'm going to flip back into my notes here. It was right there, so I'm going to grab it. That was it, right? That was our cross product? I'm just going to throw it right here so I can have it and look at it. Okay, that's just so I can look at it. What is the magnitude of a vector? Square root of each component squared and added up, right? So what's the first component squared? Sine to the 4th u cosine squared v. Second component squared, sine to the 4th u sine squared v. Third component squared, cosine squared u sine squared u. Just drop that off in there. That's just for later, okay? I mean, that's just if anyone prints off these notes, they'll know that came from the previous example. All right, does any of that clean up? Oh yeah. Check that out. This is, let's see, the first two terms. I see something on the first two terms, don't you? Factor out a sine to the 4th here and here, and that would leave you with the cosine squared v plus sine squared v, which is just going to be a sine to the 4th u, right? Plus over here, cosine squared u sine squared u. What can I do there? Factor out a sine squared u. If I factor out sine squared u, I'm left with sine squared u plus cosine squared u, which is that's just a 1, right? So this just gives you sine u. So here's what I want to do then. I want the double integral over d, right? Now, since it's over d, and d is a rectangular region. Now, we have to be careful when we say d is rectangular. It's rectangular. It's sitting off in the background, right? It's not part of our three-dimensional space where our surface is, but it's somewhere else, right? And that goes from 0 to pi, and that goes from 0 to pi. If I do it that way, I have to do du and then dv, right? That's the order I'll do it. And then in here I have sine u. What's the antiderivative of sine u? negative cosine. So we have 0 to pi. This is negative cosine u evaluated from 0 to pi dv. Cosine of pi, -1, but then there's a negative, right? So that just becomes a 1. And now what's cosine 0? 1, but then it's negative, but then that's subtracted, so it becomes +1 dv. So now we're integrating. I'll move over here so I have some more room. We're integrating 0 to pi of 2 dv, which is just 2v evaluated from 0 to 2 pi, which is 4 pi. Now the formula for the surface area of a sphere of radius r is 4 pi r squared. We got 4 pi, which makes sense because our radius is 1. If you did this problem, starting it all back up top and putting like an r in here, r, and going back through and doing the partials again and doing the cross product again and then taking the magnitude again, everything would happen. What would happen is, what would pop out there, I did this at home, is you would get an r squared sine u right here. And then it would just follow you down through the rest of the problem. Okay? I'll leave that as fun for you, maybe sometime this summer. Sit next to the pool. Something fun to do. All right. You tell me. What's the rule on switching the order of integration? Can you switch the order of integration here? Only because these are between constants, right? If one of these was dependent on the other one, like a function, then you can't switch them. In fact, because this only had u in it, you could split it into 2 integrals and multiply them using that one. Anyone remember what that theorem was called? Flex? What? Was it Claret's? All right, surface area of the graph of an equation. So what we're about to see here is that what we've done before with surface areas is just an extension of what we just did, okay? So this is a special case of what we just did when we have z equals f of x, y. So that means that our parametric function, our x component is x, our y component is y, and our z is some function of those. You could also look at this as your x is u, your y is v, and your z is some function of u and v. All right, now I'm not going to use this, but the book doesn't use this either, but that's what I'm trying to get you to see is that if the first component of the vector function is just u, the second component is just v, and then the third one is some function of both u and v, then that's just basically this case right here. And when you do all the work, which we will not show, when you do the partial with respect to x cross partial with respect to y, you take its magnitude, it will always look like this. And I don't do it, I put y here. Well, you have to go through all the work, but it has to do with the fact that what will the partial with respect to x always be? If these are the 3 components, boom, 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 right? It'll always be 1, 0, and then something here, right? But the vector will look like 1, 0, something. And then the partial with respect to y would be 0, 1, something. And then when you cross those, certain things cancel automatically because of the zeros. And you're guaranteed to have this, all right? So it's square root of 1 plus partial of f with respect to x squared plus partial of f with respect to y squared. And that means if this is the magnitude of the cross product, if that's what this is, then this double integral becomes this. So it's just a very special case. So instead of having to go through all this work of crossing and taking partials, if you can recognize this in the problem, then it's straight to here, which is nice. I'm not ready for this problem. This problem is a little bit too much for right now. So what I have is a handout for you. It's not a quiz or anything like that, but it's again trying to get you to be led up to where we're going here. If you could pass a couple of those back, please. I didn't get mine out. Just pass a couple of those. All right. One of the challenges that we have is trying to define surfaces. And the book does an okay job, but I thought I'd give you some problems to kind of take you by the hand through defining some parametric surfaces. So what we're going to do is we're going to try and come up with the vector functions for everything on this handout. This will serve you well in the next section if you can get your head around this, all right? So because I had to make copies for you, your pictures are not as good as mine. So my intention here was for you to be able to look up here and see it and not necessarily be looking there, all right? So find the vector function R of uv, which yields the disk shown below. Now, do y'all remember me saying red, green, blue, RGB, red being x-axis, green being y, and blue being z, all right? So this is our x, this is our y, this is our z. That's labeled on yours, right? But it's not up here. So I'm going to kind of spin this disk around so you can see it, right? Can you tell what the radius of this is? 2. And it's everything inside this thing, right? So let's try and come up with the vector function. Yeah, there we go. What do you think? See, here's what I want. I want to know what these need to be. And what I will do is I will label them as x, y, and z, as meaning our x component, our y component, our z component. They all have to be functions of u and v. So which is the most obvious thing to you here? What's the most obvious thing? Well, I'll take the what? The y is 0, right? Do you all agree with that? Because this disk is flat like that, your y, no matter where you are, any point on this disk, the y is 0. Agreed? Okay, so I'm going to come down here and I'm going to put y equals 0. All right, what else is obvious to you? Or maybe not so obvious. Okay, and let me ask you this. What if this was just the outer ring here? That'd be a circle, right? And how do we define circles? Well, we'd say things like x squared plus y squared is 4, or x squared plus z squared is 4, something like that, right? See, but we cannot use equations here because these have to be components of a function. So we have to be a little bit careful here with how we mess with our equations. If we look at it from the side, though, oh, not this one. I'm going to flip it this way. The reason I did it that way is because my positive x is this way, my positive z is this way. Then this looks like a circle, doesn't it? It almost looks like a polar region, doesn't it? Where my theta goes from 0 to 2 pi, and my radius goes from 0 to 2, right? So just see if you agree with this. Could I let my x, now I have to use u and v, I can't use r and theta, okay? Can I do this? Can I let my x be, let's say, v cosine u, and let my z be v sine u? And let my v be between 0 and 2, and let my u be between 0 and 2 pi. Okay, so let's see if we can get our heads around what's happening here. Remember we talked about grid curves? Like if you hold one constant, what happens? So let's just hold one of these constant. Let's hold v to be constant, and let's let v be 2. Then what would 2 cosine u for x and 2 sine u for z draw? The outside circle. It would draw that outside circle, right? What if I hold v to be 1? It would draw the circle radius 1. If I let v be 1/2, it would draw a circle radius 1/2. And if I put all those circles together and let v vary from, 0 to 2, I get the whole disk, don't I? Now what if I hold my u constant? Well, that means I'm holding an angle, right? So I'm pointed out, let's say, this direction up here like this. And then I let my v vary between 0 and 2, and what I do is I draw a little line segment that goes out to the radius. Then if I change the angle and do it again, I draw it. So there's 2 different ways of drawing that whole disk. But do you all get this? Yes? All right, so what I would do is I write r of uv is equal to v cosine u 0 v sine u, close it, and then of course those are my restrictions on u. That's the way you can draw circles in 3-dimensional space with a vector function of 2 variables. Use something like that. All right, B is a little, well, B is going to take a while. You ready? I'm going to close this real quick. I think there's something running in the background here. All right. Find the vector functions, plural, which yield the 4 face surfaces of this tetrahedron. So for those of you who have taken some physics and have done some flux and stuff like that, know about having to figure out what the surface is. Maybe it depends on, I don't know what the flux looks like in physics, but how complicated the shapes are. But here's a tetrahedron. We'll be able to compute the flux on that later, but not yet. We need to first be able to handle how to find parametric functions to represent each of the surfaces. So there are 4 surfaces, right? There's this front side here. There's a bottom. There's a back side on the right. There's a back side on the left, right? 4 different surfaces. Each one of those has its own unique parametric function that represents that surface. So now I'm going to go try and get it, all right? Get each one. So I'm going to copy this, bring it over here, new page, paste it. There you go. So what I'd like to do is label the sides. Let's call this back side over here, let's call it S1, surface 1. Let's call the back side over here surface 2. Let's call the bottom side here S3. And let's call the front side here S4. Red, green, blue again, right? X, Y, Z. Let's start with S1. For S1, I'm going to draw the surface S1. And remember, the x-axis, positive direction is out here, right? Z-axis, positive direction is up. So what I'm going to do is I'm going to draw it where the x positive is this way and the z positive is this way. Where does that appear to hit? Well, you have the points, don't you? Where does it hit the x-axis? 3, right? 3. And then where does it hit the z-axis? Up at 2. And if we look at this right here, right, then here's how I'd like to try and, well, I'm trying to come up with the vector function, right? So I need the x, the y, and the z components of this r, right? This r of uv. What do you know for sure here? Y is 0, right? Because I'm flat up against the xz plane. So y is 0 again, that's nice. My x varies, doesn't it? My x varies between 0 and 3, right? So why don't we just call the x u? And then my z varies, doesn't it? And it goes between 0 and 2, but isn't the z a function of the u, right? Or the x, but x is u. So I could get the equation of that line, couldn't I? Like I could come over here and go, all right, that is z equals negative 2/3 x plus 2, right? I could do that. But what's that? Negative 2/3, and yes, and then it would become u if u is x, right? But what I'm going to do, and this is where things can be a little bit unnatural, is I'm just going to let z be v, okay? Z is v. X is u, z is v. But what are my restrictions on u, and what are my restrictions on v? So u has to go between 0 and 3, and then v, think of this like a type 1 region. V has to be between what? 0 and negative 2/3 u plus 2. So I could have written negative 2/3 u plus 2 right here for v, but I'm writing it separately, and I'm using that restriction in the restrictions itself over here. Okay? Questions? So what is the vector function? I'm going to call it r of S1 of uv equals u0 v, and then my restrictions are that u is between 0 and 3, and v is between 0 and negative 2/3 u plus 2. Is that all right? Questions? I'll show you real quick. In Mathematica, when I want to graph things in 3D, Mathematica has this menu here. Well, it's kind of hard to see here. It says, how many different types of plots can I do 3D? I can do parametric plots, all these different things, right? If I do this one, parametric plot 3D, and I click it, it says, give me the vector components, x, y, and z. So what was the one we just had? It was u, right? I called it u, and then the next one was 0, and the next one was v, right? Then it says, give me the variables that you're using, u. Give me the minimum value of u. It's 0. What's the maximum value? 3. What's the other variable? V. And then what's it go from? 0 to what? Negative 2/3 plus 2? There it is. Okay? Now, I mean, by default, Mathematica has certain ways that it draws the x and y axis and stuff. I don't like it, so I constantly always have to change it. But that's the way it comes in, right? So I'm going to leave that there, and then we're going to do the next one now, and we're going to confirm that it draws this tetrahedron. Questions, though? You ready for S2? S2 might go a little faster, right? So S2, if I'm going to do S2, whoa. It didn't like that. For some reason, it did not want to bring it all over. Yeah, I don't think I do. That should grab it. Come on. There you go. All right, so on S2, what axes do I have here? Y and Z. And I go out, what, 4 here? And this still goes up to 2. So I've got this right here. What's my X, Y, and Z this time? X is 0 this time. Let's let Y be U, and let's let V be Z. What are my restrictions on the 2? U is between 0 and 4. V is between 0 and then the slope, which is negative 1/2 U plus 2. That was a little quicker, right? Now I'm going to call it RS2 of UV, and it's 0, 0 UV with these restrictions right here. That makes sense? All right, what about S3? It's X and Y. I think I can squeeze it on here. For S3, it's the XY plane. Where does it hit the X? At 4? Is it 4? It's 3, right? It's at 3, and then on the Y it's at 4. So you've got this, and so let's try and write it out without having to draw, or without having to list out X, Y, and Z. What's the X component? U. Which one is 0? Z. So, and then Y would be V, restriction on U, 0 to 3, and then restriction on V, 0 to negative 4/3 U plus 4, right? Okay, so far everything has been pretty darn good, right? So far. S4, which I've saved to the end, is the most challenging one. The reason it's challenging is because it's not flat up against one of the sides, right? So you can't let one of the variables be 0. So let me try and help you out with S4. So for S4, I'm going to draw a quick picture of S4. Here's my X, Y, Z. So it goes up to 2, it comes down to 3, it goes out here to 4, and then it comes over like this. This is my S4, right? Just that one. What would be really nice is if I could look at this as a surface above a shadow on the ground. Now my shadow on the ground is that right triangle, right? On the ground. And that, I know the restrictions on X and Y there, right? So can I look at that as a function up there? Well, sure, because it's a plane, right? So how do you get the equation of a plane if all you have are 3 points? 2 vectors, cross them, point in the normal vector, you come up with the equation of the plane, right? I'm skipping all that work. I'm just going to tell you what it is, all right? This plane has the equation, where is it? Comes out to be 4x plus 3y plus 6z equals 12. But does everyone appreciate the work involved in that, right? Okay. So that's the equation. Since I'm going to write my parametric equations, I'm going to let my x be u, I'm going to let my y be v, and I'll be able to control those restrictions, right? My z is now just that solved for z, replacing my x and y with u and v. So if I solve that for z and replace x and y with v, u and v, respectively, I get 2 minus 2/3 u minus 1/2 v. Do y'all follow what I'm doing here? Take that, solve it for z, move these 2 terms to the other side, divide through by 6. You get this. Replace your x with u, replace your y with v. And now we have our vector. We can come up with our vector function. It's r of s4 of uv is u is v is 2 minus 2/3 u minus 1/2 v. And our restrictions, let's write them out explicitly because I've just said what they are. I haven't written them. U's between where and where? 0 and u is x, right? What does x go between? 0 and 3, right? What's my v go between? 0 and, careful. You have to look at that ground as being like this, right? This is your x and this is your y. So you have to, it's like a type 1 region. So it's going to be, what was that, 4 up there and 3 down here? So negative 4/3 u plus 4. With me? All right. So we have parametric surfaces. We have vector functions that represent all 4 sides of that surface. Okay? So what we do later on in the next section is we say, okay, now act like there's a vector field out around this thing. And we've got vectors going into the surface and out of this surface. And we're trying to add up all the work, basically. It's like a flux. So we have to know, we have to have a vector function that represents the surface so we can figure out what's happening on that surface. So what we're doing is trying to build up to the eventual stuff we're going to do. All right, what's next on our list? Okay. Find the vector function r of uv, which yields the cylinder shown here. Kind of tough to see it on your page. Here, I'll show it to you from the side. Bring it around. Right? Got the idea? Okay. Well, what shall we do? Here's one place to start. We know that this, as a cylinder, back when we were learning about quadratic surfaces, This would be x squared plus z squared equals, it was 1, I think, a radius of 1, right? When I spun it. Right, wasn't it? Yeah, it's 1. Okay. So I know that that's the equation. Is that what I wrote on here for you all too? Okay. So that's the equation. What is the difference between this one and the first example I gave you? Look at the first example, example A. It was a disk, right? What happened was we drew the circle, and so we needed one variable u to be able to draw a circle. We needed the other variable v to come in and go out, right? Here, we don't need to go in and go out. We need to go back and forth, right? So one variable is going to draw our circle. The other variable is going to move us back and forth. So how can I draw the circle that'll be part of that cylinder? How do I draw one of those? Cosine sine, right? So r of uv, why don't I let, which are the variables that are going to be messing with here with cosine and sine? X and z, right? So how about cosine, let's use u, and then sine u. Do you agree that if I let my u vary between 0 and 2 pi, then I'm going to start drawing circles like that? Circles that'll be, I guess, parallel to the xz plane, the circle will be. Now what I need to do is be able to move that back and forth and call the y component v, exactly. And then v vary between, what was it, 1 and 4? Good. Does that make sense? If v is held constant at 1, let's say, right? If v is 1, then this is just going to draw a circle, right? So that would draw me the circle at the end down there, wouldn't it? And then if v is 4, I would draw this edge. And if v varies between everything in between, it draws every circle down the entire cylinder. Yeah, when I spun it, it was kind of hard to see, but yeah. From your picture, you can't see it. That cylinder's hollow, right? Okay. If you're asked for the surface area of this, right, then you would have to do this partial with respect to u, partial with respect to v. Then you do the cross product. Then you take the magnitude, then the double integral with those two limits of integration. Yep. Which seems a little harder than just looking it up in a book, but it would correspond to that. You know, this might be easier in a Cal 1 and a Cal 2 class with just doing a line segment surface of revolution. You know, I mean, there's easier ways to go about it. The thing is, this is more powerful because you can generalize it, and it works in vector fields better, as we'll see. It's easier to work with parametric surfaces rather than just quadratic surfaces. I don't know if that makes sense. The difference between a vector, parametric surface, is that you have a vector equation, draws it. With a quadratic surface, you have an equation that relates the variables, but no easy way to draw it by just varying two variables. Hope that makes sense. Where are we? Okay, next one. This one should be pretty quick. Find the vector function r of uv, which yields the red end cap of the cylinder shown here. It's the same exact picture. What is it? Yeah, see, I gave you this to see which one you would gravitate more towards. Are you just going to want to take this one and adapt something? Or are you going to want to take this one and adapt something? The red one has everything inside the disk, doesn't it? It's the cap. So you need one of the variables to be able to give you all that shaded space. The other variable to rotate The only thing that's different between this one and the first one is that instead of being over here at 0, you want to stay fixed. Your y coordinate wants to stay fixed at what? 4. You don't see it? So your y is going to be 4 always. So you don't need the v for the y component. So what would it be? You need the v for the what? For the radius. Good. Yep. It is. It starts to feel that way after a while. All right, so what we're going to do here for this cap, all right, for that cap, what we're going to do is we're going to let our r of uv be such that, well, what did we say for sure we knew about? The y would be what? 4, so that's not going to move. I need to draw a circle radius 1, but I need it to be able to change in radius, right? So I need to use the v to change the radius, then the u to have control over the angle, and then v to change the radius, and u to control the angle here. It's not so bad. Now u goes between 0 to pi, and v goes between what? 0 and 1, so that's my radius. You wouldn't be able to draw a solid with a parametric function of 2 variables. You could do a third, though, and you could be able to control it that way. So UVW or something like that. And then you could draw, because then you'd have a control over a third dimension. So you could basically, you could change every component you could control. See, we only have 2 variables. We have to control 3 components. So there might be interdependence. With 3 variables, you can control each one independently. Can't do it with UV, which is why we say if you have a parametric surface of two variables, it draws surfaces. It doesn't draw solids. If what? But then this, that's what I'm saying, then this would be U of VW. Yes. To answer your question, yes. But we won't do that in this class. We only go to parametric surfaces. But you could go to parametric solids. I mean, just imagine you can have a function, a vector function takes on any variables and spits out anything. Well, yeah, I mean they're hypersolids and things like that, but it's beyond the visual part we've discussed, right? Okay, where else? What else here? All right, this one's a little bit challenging. Example E. I'm going to disable that crap. I don't know what's going on there. Oops, forgot to put my code away. All right, so this is a cylinder, and it has 4 surfaces to it. Do y'all see the 4 surfaces? Oh, 3. I'm sorry, 3. I don't know why I'm saying 4. It has the blue part, right, which is like the cylinder part that's been cut. You've got this front surface here, which looks kind of like an ellipsis-looking thing, right? And then the backside, which is a circle. Y'all with me? Can we find the vector functions for the 3 surfaces shown here? Let's start with the easiest one. What's the easiest one? The backside? We'll call it S1. Come on, you can do it. S1. We'll call this blue one S2. This front one S3. Now, I gave you the equations of each of those, didn't I? On the S3, I'm just going to write this down. It was X plus Y minus Z equals 2. That's the equation of a plane, right? That's where that plane cuts through that cylinder. The cylinder was X squared plus Z squared equals 1. And then, of course, the backside is the same thing, X squared plus Z squared equals 1. So S1, quickly. R of S1 of UV is V cosine U, 0 for the Y component because you're not going to move, and then V sine U between 0 to pi, V 0 to 1. I can tell some of you are catching on to this. All right. S2 is where things get a little bit weird, okay? All right. Tell me about the relationship between X and Z. It's a circle, right? Do we need to change its radius? No. So my X and Z can just be what? Cosine U and sine U, right? Because that's going to draw me circles. The only thing that's really restricted here is this back and forth between the Y, right? Okay, so let me write this down. My R of S2 of UV, that's exactly what we're going to do. Good. We're going to say this was cosine U, the last one was sine U, and then my Y component, or Y coordinate here, is just back and forth between two things, right? So let's call that Y component, let's call it V, all right? I know my V's start to look like R's. There's my V. What's the restriction on U right now? 0 and 2 pi. Now let's discuss the V part, because this is the part that you have to be careful with. The V, if I look at it from the back side here, if I turn this, okay, if I turn it sideways like this, okay, V goes this way, right, because that's our Y. It starts out at 0, right? How far out does it go? Well, until it hits that edge, right? Or down here it hits that edge, or down here it hits that edge. Or on the back side, it hits up here at this edge. What is that edge controlled by? It's controlled by this, right? That plane. Z, x plus y minus z equals 2. So what about if I take, was that the right equation? Yeah. What if I take that equation up here and solve it for z? Solve it for y. Thank you. I'm glad you pointed that out. We're trying to figure out what the y is, right? Yeah. Right? Our y is the one being controlled. So solve that for y, and what would you get? 2 minus x plus z, or plus z minus x. Right? But what's x for us? It's cosine u, and what's z? Sine u. So my v needs to always be stuck between 0, which is the back side, right? And 2 minus cosine u plus sine u. You can see these start to get a little bit odd, but how about S3? This will be the last, all we have time for. I told you it's hard to get through this section. One day isn't even enough. Okay, what about the next? S3. Let's see if I can fit it in here. I'll try and help you. Look at this. Look at it from this side, right? It's solid, isn't it? It's a circle, basically, that's solid. What's changing, though, is that y coming in and out, right? It's still trying to draw a circle with everything in between, but the y keeps changing. So how am I going to draw a disk, everything in between? How am I going to do that? What's the only way we know how to draw a disk? V cosine u, V sine u, right? You need both variables u and v to control the whole, right? This whole thing and the rotation. So I have really no choice here on S3 than to define which two components are going to be the part that's the circle? The x and the z. So I'm going to define the x to be v cosine u. I'm going to let this one be v sine u. But my y component is what? I can't use v. I'm already using v, right? But the y is this, isn't it? Isn't it 2 minus x plus z? And I know what x is, and I know what z is. So I can just call it 2 minus x v cosine u plus z v sine u. And then, what's our restriction? U is between 0 to pi, and v is between 0 and 1. And that draws that one. Zero and what? It's the radius of the circle. Remember, I want to draw the circle out. V is controlling my radius. That okay? These take some getting used to. I'll show you real quick in this. If I open up my code for this, you can see right here the one we just did. Right? That's it. V cosine u, 2 minus V cosine u plus V sine u, V sine. Here's my restrictions. U is 0 to 2 pi, V is 0 to 1. And what did it draw? Well, it drew that thing right there. This right here. All of those are my different parametrics. Now, I know we still have 30 seconds. Remember the formulas I gave you? Somewhere down here, after divergence, after greens, are common parametric surfaces. Cylinders. Okay? Cylinders. If you want to draw a cylinder with a certain radius, that means not the inside, then what you do is, like in this case, this is our x component. That would give me my circle. The x and y here would give me a circle, radius a, right? And then letting this be v means it opens which way? It goes up and down between my restriction on whatever v is. If I do it this way, instead, I draw a cylinder, right? Radius a going out which axis? The y-axis. And then this one will go out the x-axis. Here's the spheres. I didn't do a disk, did I? No, I didn't. I should have. Maybe next time. But I still want to talk to you about a vector equation for a plane. As of right now, the only equation you know for a plane is a times x minus x naught plus b times y minus y naught, you know. But there is actually a vector equation for a plane. So maybe we'll touch on that next time. We're gonna have to keep going. I don't know. We're not done with this section. I'll look at the homework assignment. I'll send something out in email for you to look at. Have a good day. See if you can finish these on your own. I'll offer it as bonus. If you can finish F and G, do next time. Yes, let me stop this real quick. Uh-oh.